Yeah. So hello everyone. I'm Pawan Kumar Raikwade. So this is the problem solving session on the course Functional Analysis NOC 23 MA 15, and we are on the week 7 now. Okay. So I'll be solving some sample problems here on the assignment so that will be helpful for you to solve the whole assignment. Okay. Let's go. Question number 1. Which of the following statements are true? Okay. Some functions are given and some spaces are given. We have to check whether these functions belong to these LP spaces. Yeah. Okay. First one, fx equals 1 by root x. We have to check whether f belongs to L101 or not. Okay. So we are going to use the monotone convergence theorem here, MCT. Okay. Monotone convergence theorem. It states that you have suppose fn's a sequence of functions uh, from x to suppose 0 infinity, such that fn's converges to f pointwise and Fn is a monotone sequence. All Fn's are integrable. Then that is in LP, suppose. I mean, integrable means. Then what you can do is you can interchange the limit. The limit of integral Fn is same as integral of limit Fn. Yeah. Okay. So yeah. So I'll find this limit of 1 by root x using these things. Okay. So you can see 1 by root x when defined for all x with just a minute. Sorry. Hello? Hello? अरे तो फॉर्म तुला दिलेला ना मी एक तो सबमिट करा केलं नाही केला का तू याला CCW ऑफिसला अरे तो सबमिट करशील रे लवकर आज मी आता सुजितला कॉल केलेला मला त्यांचा मेस रजिस्ट्रेशनचा मेल आलाय माझे मेस रजिस्टर झाले तर माझे सगळे पैसे झाले ते 20,000च्या आसपास हा. आता उघडं असेल मला वाटते ते कारण मी मागच्या वेळेस मी गेलेलो तेव्हा विमला मॅम आता अवेलेबल होती तिथं नाही आता जस्ट हो आता तिथं लय वेळ झाला असेल नाही का हो मला वाटतं 5च वाजले आता इथं तू उद्या एकदा चेक करून बघशील उद्या पण असू शकते तिथं दुपारच्या वेळेला 11च्या आसपास नाही काय हरकत नाही सुजितला आठवण करून द्यायला हवं होतं मी विसरून गेलो मी जाऊ दिसेल काय नाही बघ उद्या जाऊन ठीक आहे सामान पण तिथेच आहे का राउटर नाही काढला का तुम्ही अजून अरे राउटर काढा रे तिथलं तिथं आज साईडच्याच रूम मध्ये आहे रे राउटर ते घेऊन जातील रे ते राउटर घेऊन जातील रे साईडच्याच रूम मध्ये काढून घे बरं आता लवकर जाऊन पण ते अच्छा लॉक आहे ना रूम हा रूम लॉक आहे मग काय हरकत नाही तरी काढून ठेव हा हा ते फोडायचे लॉक चल मी ठेवतो मी तर सेशन रेकॉर्ड करतो NPTEL चा मी करतो नंतर कॉल मी पुढचे बघितलेत ते सोपे आहेत काय नाही मी एक्सप्लेन करून टाकतो चल बाय बघ इम्पॉर्टंट काय ते बघ आधी तर राउटर काढ बाकी बघता येईल नंतर चल. Yeah, hello. Yeah, I'm sorry for that. I had to receive a call. Okay. So we can interchange the limits here. Yeah? So here 1 by root x is defined on whole 0 to 1, and you can see as x goes to 0, this value, diverges to infinity. So there's a problem. We cannot just directly say. Yeah. But what we can say is, if I define fn's as fn at x equals to same 1 by root x, but this time this is only if 1 by n less equal x is less equal 1, and before that it's 0. Yeah. So now what happens is integral over 0 to 1 fn x dx. Okay. Like Lebesgue measure here, which will be same as integral 1 by n to 1, because it's before it's just 0. Yeah. And this is just a Riemann integral. You know this thing. This is maybe 2 root x from 1 by n to 1, which is 2 minus uh, 2 by root n. Yeah. So now we can say the claim is this sequence of functions fn's converges to a given function f pointwise. That can be seen, not a problem. And fn's are monotonic. Yeah, you can check their monotonic sequence. I mean, fn is a monotonic sequence. Monotone sequence. Yeah, it's a monotonically increasing sequence, I hope. Yeah. So that implies now by monotone convergence theorem, integral of f is just integral of, I mean, limit of integral of fn, which is limit of what is integral of fn? 2 minus 2 by root n. And as n goes to infinity, it is 2. Yeah. So this is finite, integral is finite, and f belongs to L1. Okay. So now the second one, fx equals to e power minus x by x. B f of x equals to e power minus x upon x, where x belongs to 0 to infinity. Okay. So, if suppose if f belongs to L1 of 0 infinity, that means f belongs to L1 of 0 1, correct? Yeah. So, but what happens is e power minus x is this graph. Yeah. So suppose this is 1, so this value, yeah, this value is e power minus 1. So for all x belongs to 0 to 1, what do we have? E power minus x is greater equal e power minus 1, which implies e power minus x upon x is greater equal e power minus 1 upon x. Correct? This is happening. That means if f belongs to L1 of 0 1, that implies e power minus 1 upon x belongs to L1 of 0 1, but this is wrong because this function is not integrable on 0 1. Yeah? Hence, f doesn't belongs to L1 of 0 infinity. I hope that's clear. The third one. Yeah? Sorry. Okay, so third one is easy. You can check. Third one is itself not integrable on 0 to 1, so not on 0 infinity. Yeah, that I leave as an exercise. This one is wrong. Okay, similar lines maybe will work. Okay. Now the second question. Hmm. Part A. Okay, you have Fn going to F in LP over mu. Then you have Gn going to G in LQ mu. So, sir have taken in lectures, sir had proved this thing that F belongs to, if F belongs to LP and G belongs to LQ, then FG, the product belongs to LR. Okay, this sir has proven. In fact, the norm of the product, the R norm of the product is less equal the F norm of P norm of F and Q norm of G. Okay, this sir had proven in the class. So what we have to do, we have to check is whether FNGN converges to FG in LP or LR, LR, sorry. Yeah, this we want to check. Yeah. Let's try with the norms. R norm, which is I'll just add and subtract maybe FGN, which is norm of Fn minus F at Gn, uh, R norm plus, I mean, less equal, this is by triangle inequality, plus norm of F times Gn minus G, R norm. Okay, what we have, Fn goes to F, Gn goes to G, right? Okay. So now this is less equal norm of Fn minus F P norm times norm Gn Q norm by this inequality here. Fn minus F belongs to P and LP plus this guy is less equal norm F P norm plus norm Gn minus G Q norm. Yeah. So here, since now Gn is a convergent sequence, right? It converges to G. This implies this norm is bounded. Yeah. And Fn goes to F, so this goes to 0. This is a single element, so no issues, and this goes to 0. So whole quantity goes to 0, so we are done. Which implies Fn converges to Fg in LQ, sorry, LR. No, okay, yeah, good. First one is okay. Yeah. Then the second one, uh, second one says Fn goes to F weakly, Gn goes to G in 2 norm, then integral Fn Gn goes to integral Fg. Okay, let's see. B, what do you have? Fn goes to F weakly, Gn goes to G in L2, and that's all. So G in L2, okay. So integral Fn Gn we want to check. Okay, so let's see what is integral Fn Gn minus Fg. And this is maybe again the same thing if we can do. Uh, Add subtract Fng maybe integral Fng minus Fng plus Fng minus Fg, okay, which is integral Fn times Gn minus G plus mm, plus Fn minus F times G. Yeah? Yeah, so this is already, this is pre-assumed, okay, d mu and all. So I can just separate these two integrals maybe. So now this integrals by Schwarz inequality. This is less equal norm Fn, maybe 2 norm, and then norm Gn minus G also 2 norm. Plus again this integral also I can do the same thing, Fn minus F. Oh, okay, I don't have to do. Hmm. Yeah, so what's happening here is Fn converges to F in norm, So, and it's in Hilbert space, so this is bounded. Fn is a weakly convergent sequence. Yeah, so this is a bounded, and Gn goes to Gn goes to G into no. So this goes to 0. What happens here is, see, Fn converges to F weakly. Yeah, which means for every phi belongs to L2 dash, phi Fn goes to phi F, or equivalently, phi of Fn minus F goes to 0. Yeah, because Fn minus F goes to 0. Okay. So now if I define phi function as phi of every element G equals to integral of or phi of any element H equals to integral of Hg. Yeah, G is a fixed element. Okay, I'll call it phi G. Okay, so this is a linear functional. No problem. This phi belongs to L2 dash, continuous linear functional, which means what will be phi G of Fn minus F, integral Fn minus Fg. And since Fn converges to F weakly, this should go to 0, and this goes to 0. Yeah. So we are through. Fn goes to Fg. Okay. So this second option is true. Yeah. The third one now. Fn goes to F in LP, and Gn is bounded sequence in infinity converging to G almost everywhere. Then Fn Gn converges to Fg in LP. Okay, so this is also true. We'll see how. Okay, I will do this thing. But like similar lines proof it is. Okay, we'll see. Yeah. So do you have Fn converges to F in LP, and Gn is bounded. Gn is bounded in L infinity, and Gn converges to G pointwise. Yeah. So with this information, the claim is Fn Gn, this product sequence goes to Fg in LP. Okay. So you get a you take a convergent sequence from LP, take a bounded and pointwise convergent sequence from L infinity, and the product also converges in LP. That's great. Let's see the proof. See, Gn is bounded like almost everywhere. When we say in L infinity something is bounded, so it's always almost everywhere. So mod Gnx is less equal M, suppose for all what do you say x almost everywhere. So but this also implies that mod Gx is also same bounded function. Okay, like almost everywhere. Okay. Now consider what is norm Fngn minus Fg p norm. Okay. So again, adding and subtracting maybe Fgn. So what we get Fngn. Okay, I'll just write directly Fn F maybe, and I'll left with Gn p norm plus norm of F times Gn minus G, I guess. Yeah, yeah. Fgn here, Fgn here. Yeah, it's subtract correct. Fg. Yeah. Okay. So yeah. So we consider these guys separately. Norm of Fn F Gn p norm raised to p. What is this? This is integral of modulus of Fn minus F raised to p to mod Gn raised to p. Yeah. So, but this quantity is less equal as mod Gn less equal p. This is m raised to p into integral of Fn minus F raised to p. But this is norm Fn minus F raised to p, which goes to 0. Yeah. And the second one, the F times Gn minus G. Okay. So this follows from dominated convergence theorem. Actually, you can check now. Dominated convergence theorem implies that the second quantity norm of F times Gn minus G goes to 0. Yeah, you just have to take the bound with, because mod f only you will get Gn minus G, you can by triangular inequality it will be less equal to m power p, that is integrable, since by dominant convergence theorem the whole thing is integrable and converges to 0. Yeah. So we are done, this thing also goes to 0. So f and Gn goes to fg in LP. Yeah, okay, cool. So, okay, just a minute. Yeah, okay, so question number third. So what we have a measure space X S mu, P from 1 to infinity strictly less. Which of the following statements are true? Okay. So Fn goes to F in LP, then Fn goes to F pointwise almost everywhere. Ah, no, this is in fact true for L1, I guess, but not everywhere. You can check with the neck counter example, which will work for every maybe LP. This is true for subsequences, in fact, but I'll give you maybe counter example. If we take Fn to be characteristic function of n minus 2 power k upon 2 power k to n minus 2 power k plus 1 to 2 power k. Yeah. Where k is such that n less 2 power k is less equal n is less equal to power k plus 1. Yeah, I hope this will work. Is it to work? Power k. I guess 2 power k plus 1 should be there. Hmm. Yeah, yeah. Yeah, like for maybe for n equals to 1, what will you need? K also, k should be 0. Yeah, yeah, this should be strictly less one side. Yeah, now k should be 0 only is the only possibility, because 2 power 0 1 is less equal 1 is strictly less than 2. Yeah. For n equals to 2, what will be the value for k? 1 only. K should be equal to 1 only, because 2 will be less equal to strictly less than 4. Yeah. This is now like nicely defined sequence of functions. The good thing about the sequence of functions is, see, measure of this set, this characteristic this set. Okay, it's always two. Oh, sorry, what 1 upon 2 raised to k. Yeah, I guess. Uh, yeah, and it's kind of dependent of n. So you can show that this Fn converges to 0 in LP, but doesn't converge pointwise. Okay, you try showing this thing. This will be an interesting exercise. Now the second option, Fn converges to F in LP, let epsilon positive, then this limit of uh, measure of this set is 0. Okay, we'll call this set as maybe A epsilon something, and set of all x belongs to capital X such that modulus of Fnx minus Fx greater or equal epsilon. Like maybe I hope this is for all in large natural number, because then what's n? Ah, oh, okay. No, no. The set is depending on n, so maybe n epsilon. No. Mm, what should I call this set? It depends on epsilon as well as on n. No, epsilon is fixed, right? Yeah, epsilon is fixed. Maybe just an. The whole x belongs to capital X, other mod of nx minus fx is greater or equal epsilon. Yeah, for a1 there will be some x's, a2 there will be some x's. Yeah, that's fine. Yeah. This is a1. So what we want to show is claim limit as n goes to infinity, measure of the set an is 0. Yeah, this is what we want to show. Okay. So the first thing is fn goes to f in LP, which means integral of modulus of fn minus f raised to p goes to 0. Okay, but integral from integral over whole x modulus of fn minus f to the power p is always greater or equal integral over the set an modulus of fn minus f to the power p. Okay, but this guy, because fn minus f is greater or equal epsilon, this is greater or equal epsilon power p into measure of the set an. Okay, yeah, this means measure of the set an is less equal 1 by epsilon power p integral over x modulus of fn minus f to the power p. Now epsilon is a fixed quantity and this term goes to 0 and the whole term goes to 0. Yeah, so we are done. Measure of an goes to 0. Okay, here we'll go to the next question. That fn converges to f in L2 and norm fn goes to norm f, then fn converges to f. Ah, okay. No, fn converges to f was in weak topology. Okay. So the C function is if fn goes to f weakly and norm fn goes to norm f, then fn converges to f in L2. That's the question. Yeah. Okay, let's see. Norm of fn minus f. You can try. Maybe this is always true in an Lie Hilbert space. That's a different exercise you can go through. Now we'll just uh, prove with respect to L2. Okay, so what is this? This is integral over x modulus of fn minus f raised to p d mu. Mhm. Okay, no, squared. Yeah. Okay, so I'll just square this guy, which is equals to integral mod fn squared plus integral mod f squared plus not plus minus 2 times integral fn f. Correct. Now, yeah. So mod fn. Oh, so what is this thing? This first quantity is just norm fn squared. The second quantity is norm f squared, and the last one I will keep as it is f and f. Yeah. So same as before, you can think of the function phi f from L2 to R as phi f of any element h equals to integral hf. Yeah, this is a continuous linear functional, and what we have is fn converges to f weakly. Yeah, that means phi f of fn converges to phi f of f. Yeah. That means what? Integral f and f converges to integral f, which is just norm f squared actually. So what do we have? We have norm of fn minus f 2 squared here is it goes to see norm fn squared plus no so again this norm fn squared goes to norm f squared. That's given plus again norm f squared minus 2 times this integral f and f goes to normal square. So 1, 1, 2, 0. Okay. Yeah. So the part C is also true. Yeah. So an exercise will be to show that this is true for all. This is true for any Hilbert space. Like you have a sequence of elements which converges weakly to another element u, and also the norm of those element converges to norm of that another element norm u. Then the original sequence converges in norm. Okay, so an exercise. Yeah, yeah. Okay, this is question number 3. Now go to question number 4. Hello. Yeah, there was some problem in the iPad. Okay. So the fourth one, the for all n belongs to natural numbers, define fn as characteristic function of n to n plus 1. Which of the following statements are true? Okay. First one says fn converges weakly in L1 infinity. Fn converges weakly L1 0 infinity. So if that's so, then what does that mean? That means for every phi belongs to L1 0 infinity, what do we have? Phi of fn converges, right? Converges to phi of something. But as you know, like L1 dual is identified with L infinity, right? And that means what is phi of fn? Like there exists a g such that integral fn g, right? For some g belongs to L infinity. Actually, it's uh, like two-way relation. Like there, for any g, we can define a functional. So what we are getting is for all g belongs to L infinity, integral fn g converges. Yeah, 0 to infinity. That means integral anyway fn is from n to n plus 1. Integral n to n plus 1 g converges. Yeah, but this is absurd. You can take a function, define a function so that this never converge, and g still is in L infinity. Try to define such a function, so this is wrong. Okay, so we'll go to option number B. The sequence fn converges weakly in L2 0 infinity. B. Okay, so yeah, what is L2 dual? It's again L2. Okay. So converges weakly means what? For every f, if I consider on L2 dual, so I should get phi of fn is B convergent, right? That's what I want. But let's see, any for every like f belongs to L2 dash, like I'll get G belongs to L2 again, such that phi of fn equals to integral fn g. Yeah, I just want to show that this converges. So what is integral f and g for g belongs to L2? This is integral n to n plus 1 g. Yeah, but this is less equal integral n to n plus 1, yeah, n to n plus 1 modulus of g squared, right? Yeah, by uh, by Schwarz inequality, Cauchy-Schwarz. And since mod g squared, I mean g belongs to L2, which implies integral 0 to infinity mod g squared convert. This is finite. Hence, this quantity should go to 0. This kind of tail of a sequence, yeah, kind of. You can imagine that. So this has to go to 0 as it goes to infinity. That means Fn converges weakly to 0 in L2 0 infinity. Okay, I hope that's clear. The sequence Fn weak star converges in L infinity 0 1. Okay, so let's see. Third. So when we are saying Fn converges, like the claim is Fn converges weak star in L infinity 0 infinity, right? That means we are taking Fn which belongs to L1 0 infinity, and we want to show that oh no, wait. What do I want to show? Fn converges weak star in L infinity. So yeah, Fn's belong to L1 dash actually. Is that correct? Yeah, so Fn should belongs to L1 dash. So when we say Fn converges like to something, Fn converges in weak star topology if and only if like for all g belongs to L1 0 infinity, the integral Fn g converges. Yeah. If this happens, then we say Fn converges in weak star. Okay, so let's see what is integral Fn g for g belongs to L1. Same as before, that is from n to n plus 1, just g. And this is less equal n to n plus 1 mod g. Yeah. But since g belongs to L1, this goes to 0. Yeah, that means Fn converges weak star to 0. Yeah. Okay. Yeah, that's true. Fourth, B and C are true. Okay, then I'll just jump to seventh. The fifth and sixth one is kind of similar, and one was already explained in the class, I guess. So I'll just go to the seventh one directly. Okay, just a minute. I'll do some. Okay. So question number 7 says X S may be a major space and let W be a proper subspace of L phi by 3 mu. And phi is the linear functional defined on W whose norm is less equal 1. Then which of the following statements are true? There exists a G belongs to L phi by 2. Oh, by the way, let's see. Phi by 3 plus what should be 1? X should be 1 minus phi by 3. So it will be 3 minus. Hmm. Oh, wait, this is not decided. This is 1 by P, so 1 by 5 by 3. Okay, so this is 1 minus 3 by 5, which is 2 by 5. Okay, so if P is 5 by 3, Q has to be 5 by 2. These are the complex exponent, sorry, conjugate exponents. So what is L for here? My P is 5 by 3, Q will be 5 by 2. Okay, that's what I would write the whole 5 by 3, 5 by 2 all the time. So my phi function belongs to W dash, yeah. But by Hanbanach, you can extend. There exists some psi, I can call it, belongs to LP dual, yeah. Such that norm of psi is same as norm of phi, yeah. But like we know LP dual is LQ, yeah, which implies there exists some G belongs to LQ such that psi of f equals to integral fg for all f belongs to LP. Yeah. So, but for all f belongs to W, what is psi f? Is same as phi f, and here it is same as integral fg. Yeah. So we get a g satisfying this thing, and anyway, like norm of g will be same as norm of g. Q norm will be same as no, operator norm of this psi, and operator norm of this psi is same as operator norm of this phi, because that's the Harmonic theorem. Yeah, we extend preserving the norms. And then operator norm of this phi is just supremum over all f belongs to W because it's defined on W. F p norm less equal 1 modulus of phi of f. Yeah, so we got the one. The question is nothing but just the interpretation of actual Harmonic theorem and the duality theory of that LP dual is LQ. That's all. So the option 1. Yeah, the second thing is interesting that if such a G exists, then it is unique. Yeah, yeah, that's an interesting thing. Okay, so okay, we'll just maybe yeah, the observation here is the space is strictly convex. Yeah, this is strictly convex. I mean the LP. So what do you, if you just immediately you should recall it in a strictly convex set, the sorry, in a strictly convex set, you take any closed and convex subset, it has a least, it has an element of least norm. Yeah, that we know. So I'll just define a new set H, maybe as okay, uh, yeah, spaces whole like for all P. So I'll define set of all G belongs to LQ such that mm, so that integral of Fg is equals to phi of f for all f belongs to W. Yeah, is that good? Yeah, this H is non-empty, we know from part A that because the extension of phi will be there in this set. Yeah, like psi will be the extension and corresponding to psi, we get a function G belongs to LQ, so that this everything will hold. Yeah, so H is non-empty, and for any G belongs to LQ, what we have is norm G Q norm will be less equal, sorry, will be greater equal. Okay, I should do some naming. Maybe. Okay, I'll just call it maybe phi. This phi. Operator norm of this phi. Yeah, this you should verify. Yeah. And in particular, actually, this set H is a collection of all extensions. Yeah. If you see, G is a linear function. G is kind of identified as a linear functional on NLP, which is uh, restriction, which is the extension of phi from this. Okay. So these are all extensions of function phi, but not necessarily non-preserving. You are just taking all the possible extensions. The claim is that the H is convex, that's clear, and closed. Okay. So if H is closed and convex, then we know that there exists least element of sorry there exists a unique element of least norm, and you know that the extension of phi already is there. So there will be the only one possible extension. If we show that this H is closed and convex, then we are through. There will be only one unique extension preserving norm of phi. Okay. So let's see if this convex. It is closed. That's clear. Sorry, it's convex. That's clear. For closeness, okay, I'll define maybe a function psi f on LQ linear functional as psi f of any element g equals to integral fg. Okay, okay, psi may not some different function. Or okay, this sigma g maybe. Why not? G sigma f. Yeah. So what is this set H? If you see, the set H is intersection of psi f inverse of uh, singleton set phi of f. Yeah, where all f belongs to W. Yeah. So the psi f is a continuous functional, and hence phi of f is a singleton set. So it's a closed set. The inverse image of closed set under a continuous function is again closed, and you are taking the arbitrary intersection. Hence, which implies H is closed. Okay, you should verify it once everything argument. So it's just an observation. Okay, so hence H will be a closed convex subset of a strictly convex space. Hence there exists a unique element of least norm, and that will be our extension. Yeah, so the second option is also correct. If such a G exists, then it is unique. Yeah. So for any subspace, a norm-preserving extension is unique on LP. Yeah, that's good. Okay. So now we'll see the question number 9. Just a minute. Yeah, okay. So now we are on question number 9. It says, which of the following statements are true? First one says the space C01 is a closed subspace of L infinity 01. Okay, is that true? Okay, see. C is the one with respect to supremum norm, it's a Banach space, right? Like infinity norm is Banach space Hence, there's no point. Banach space, hence it's closed in L infinity. Yeah, thus for the other two spaces L2, L1, C01 is not closed. Actually, it's dense. I mean, CC over 0. Yeah, space of all compact the continuous functions with compact support is dense in L, like P maybe 01 P strictly L1. Yeah, and CC01 is contained in C01. So C01 cannot be closed. These two options are wrong. Yeah. Okay. So question number 9 is settled. So question number 10. Oh, oops. There is no question number 10. We have to check whether which one of the following three are correct. So first option says G belongs to L infinity mu and let TF is okay. Same everywhere. Ah, okay. So first option, whether T belongs to L1 mu to L1 mu. Okay. So let's see. Try to find out L1 norm of TF, which is integral modulus of GF. Uh, okay. Where F belongs to also. Okay, G. Okay, this is less equal norm G infinity into norm F1. Okay, so by um, what is that? Uh, yeah, some inequality. Okay, this follows. Modulus of norm is less equal norm fp and norm fq. Like one p norm, one q norm. Here p is one, q will be infinity. What is this inequality? Yeah, okay. So hence norm of tf is less equal some constant times norm f for all f belongs to L1. Yeah. Hence this is true. Yeah, T is a bounded linear operator. How about the second? Like if f belongs to L2 mu, yeah, again T is sending every element to L1 space. So we have to take one norm of TF, which is integral modulus of GF, and this is again this equal norm G infinity, norm F one norm. So this one norm like can be related to two norm, like we cannot say, because what we have needed is this should be less equal some constant actually times norm f2. Yeah, but we cannot express this quantity in terms of 2 norm of f. Yeah? So I don't think this is wrong. The third one, that g belongs to L2 mu and tf equals to gf, again the same function, and this time is okay. Oh, here g belongs to L2. Okay, before that g was belongs to L infinity, and here g belongs to L2. Okay, so yeah, because now the functions are in same space. Now if I consider norm TF, okay, one norm, which is integral modulus of GF by Cauchy-Schwarz inequality. Now this is less equal G2 norm and F also 2 norm. Yeah, so this works. For every F, norm TF is less equal some constant times norm F, implies T belongs to a set of all linear operators of L2 mu to L1 mu. Yeah. And all the like, functions are well defined, that's clear because of this inequality straight away. Yeah, it's finite and linear operator. Okay, the third one is also correct. So this is done. Assignment, which one it was? Assignment 7 is done. I hope you understand everything. If you don't, if you have any doubts, you can ask.